Bonjour Pascal, tu peux nous entendre?
Oui, tout à fait.
Parfait.
C'est bon. Bonjour.
Euh,
Bonjour Pascal, ça va?
Salut Rob, ça va et toi?
Ah oui, ça va, mais c'est un peu tard. Donc
Oui, j'ai vu.
je ne sais pas si je suis pas sûr que je reste pour tout le temps. Ok.
Tu vas-
Ah, ouais.
C'est vrai que c'est l'heure de dormir, hein. C'est pas les
Ah
mêmes
oui,
heures.
je suis fatigué en plus en fait, puisque j'ai pas mal fait aujourd'hui. Mais
Ah oui,
bon, ça va?
ça va,
Paris,
ça
ça
va.
va bien?
Ouais, bah écoute, voilà, rien de, pas grand-chose de spécial, sinon que je vais prendre un détachement, là, je vais aller aux
ah,
mines. Je vais aller
I,
retrouver
I, I
Silver.
get the point. You're discussing together, right?
Yeah, exactly. You can ignore
Okay.
us.
Salut Tarek.
Uh,
Voilà, rien de, pas grand-chose de spécial,
Hey
sinon
James, how are you?
prendre un détachement.
Morning.
it's okay.
It's not morning for me, mate.
Oh yeah, good evening. Actually, I was thinking about it, Rob. I had a hockey game last night and it ended
Yeah,
at like 7:30.
Hi James.
Morning, morning. And
That,
when I went to
il
bed, Rob, I
faut
was like,
arranger
oh,
le son
Rob's
ici.
up already.
exactly. Yeah.
Oh yeah, good evening. Actually, I was thinking about it, Rob. I had a hockey game last night and it ended at like 7:30.
Hi James.
Morning, morning.
That,
When I went to
il
bed,
faut
Rob, I was like,
arranger le son ici.
it's looks like our audio is messed up.
Might be okay now. We'll see. I certainly heard about your hockey game multiple times.
Yeah.
Et où est-ce que je peux me brancher? Ok. Ah, ou l'autre. Enfin, c'est bon? Super. Ouais. Ah ouais, j'avais pas vu. Mais il le branche là. C'est bon. Can you hear me? Hello? Hello, everybody.
Salut Alcia.
Perfect, salut.
Salut, SEO.
Ah, it's not charging? Il charge pas. Ah, ok. Sorry. Ah, it doesn't work. Ouais, il marche pas.
Ouais.
Ça ne charge pas. Il faut les deux.
C'est bon, ça.
Mais c'est le chargeur.
Non, non, je sais, mais on peut le charger directement
Ça
d'ici.
te dérange pas de te connecter, toi, alors parce que moi, j'ai peur que.
Non, non, il a un chargeur.
Ah, il a un chargeur spécial.
Ça marche pas, non? Ouais. Peut-être une prise qui marche pas. Ok.
Oui, c'est bon, ça marche. Parfait. Qu'est-ce que je peux faire, moi? Est-ce que moi, je dois faire quelque chose? C'est bon, là? Ouais. Et donc, moi, je dois couper mon audio, peut-être?
Ouais. Can you all hear me?
Yes.
Okay, so we're going to start.
Oui, tout le monde, tu le mets dans un petit coin, et après, tu fais mort, ici,
Ouais, après,
et tu fais cacher le...
ça, je peux enlever ou...
Tu fais mort ici, hein, clique sur mort.
Ouais.
Hide vidéo panel, hide name, another, tu fais tout cacher, et après tu le remettras à la fin.
Non. Ah oui, ok. Mais
Et
là, je peux enlever ou...
lui aussi.
Comment hide name, c'est dans les... Non, c'est pas ça. Je sais pas. Je pense que ça va disparaître tout seul, non? Un truc.
Non, regarde. Non, mais c'est dans mort, c'est là.
Non, je sais pas où est-ce que c'est. Non, c'est pas grave.
Moi, ça m'embête un peu. Attends, c'est... Fais du show vidéo panel. Bon, ça, c'est celui-là.
Ouais, ça, c'est
D'accord.
juste le truc. Ça disparaît pas, en fait.
Si. Donc, fait hide vidéo panel.
Ouais.
Et ensuite, on lui... merde.
Ok, have to start, en fait, on peut pas arrêter.
Allez, c'est parti.
Is your mic on or off?
No, I asked you.
No, but I said in the beginning you could do it yourself.
So what I have to do to put my mic on?
Yes, I remove mine.
Okay, sorry. So, but we have a feedback now. So I just introduced everybody. So you didn't hear me, but I'm not going to repeat. I just say who you are, where you are working, and I was just finishing with Tarek and giving the stage to Tarek Bouazza to have 45 minutes to defend your pitch.
Okay. Thank you to the jury members for being here today and for the ones that are online with us, and thank you all for the audience. So my name is Tarek Bouazza, and this is my PhD thesis defense presentation, and the title is Contributions to Geometric Observer Design for Visual Inertial Navigation. Okay. So this has been a 3 years long project. We've done a lot of work and a lot of contributions that I will present later. I will first start with some motivations that led to these contributions. So the problem that we're dealing with itself is the problem of autonomous navigation. So the challenge of autonomous navigation is predominantly present today. And for robots, it's quite challenging to perform perception, navigation, or mapping tasks in diverse environments. And so one of the backbone of autonomous navigation nowadays is what we call state estimation. And this enables robots to accurately determine their navigation states. So that's their position, orientation, or velocity, which is essential to operate in unknown environments. So why visual inertial navigation? So it basically comprises of 2 types of sensors. So the first sensor is a camera. So it's a lightweight, cheap, and easily accessible sensor, and it provides us with rich visual information on the environment. And then we have an IMU, which is an inertial measurement unit, which provides us with measurements on the motion of the robot itself, and that's angular velocity and acceleration of the vehicle. So these 2 sensors are complementary, and if we combine the measurements, then that will lead to low cost and highly accurate navigation systems. Okay. So visual inertial navigation is well suited to many applications, so like micro aerial vehicles, autonomous driving, underwater exploration and different underwater applications. Also, it's present in wearables and health tracking devices, and in augmented reality and virtual reality experience more recently. So why geometric observers? So what we mean by observer or a filter, it's an algorithm that is designed to estimate the states of a system from incomplete or noisy measurements. So in general, we have a system which is a dynamical system that we have, and we want to design an observer, which is this algorithm that will estimate the state of the system. And we usually, in order to do that, we have to sort of design the estimate such that the error between the estimate and the state goes to zero or converges to something that we want. So in the classical designs, the system itself is a nonlinear system that we're dealing with. And in the classical design, we have this form of observers where we basically have an internal model of the system itself. And we have this term over here, which is the correction. And this term is designed such that this estimate and the difference between this estimate and the state converge to zero. But the problem is with this type of errors is not very suited when the state of our system itself lives in a manifold. So it's not really in an Euclidean space. And what happens is that this difference error is no longer well suited for this type of problems. So luckily for problems in robotics and navigation in general, the states for these problems actually live in a specific type of manifolds, which we call Lie groups. So what we mean by a Lie group is that it's a manifold that also has additional structure. And this structure is that, for example, we can multiply elements in this group in order to generate new elements. And we can also invert elements. And if we multiply an element by its inverse, we get the identity element, which is sort of the central element in the group. And so what geometric observers mean, it means that we can exploit the structure of these Lie groups in order to handle the nonlinearities of these problems and to improve the estimation performance of our observers. Okay. So in the introduction, I spoke about visual inertial navigation. And when we talk about vision, there are three particular problems that are of interest with monocular vision. And the first problem that is quite popular is the PNP problem, or the perspective endpoint problem. And in this case, we have a camera that is viewing some landmarks in a 3D environment. And we have information about the positions of these landmarks in the environment. So, and this problem is called the PNP. When we don't really have the measurements of these coordinates in the 3D environment, we actually talk about relative pose estimation. So we're basically estimating the pose of a camera with respect to some other frame. There is a frame of reference that is like an initial frame for the camera. And as the camera moves, we estimate its pose with respect to this frame. Now, when the landmarks happen to lie on a planar surface, then we talk about homography. So the way this problem is solved is we estimate this homography matrix, and then we decompose it to extract the relative pose between the two frames. So a particular focus of this thesis will mainly be on the last part, which is dealing with homographies for this type of problems. Okay. So there's a set of contributions that I want to discuss in this work. So the first two contributions are essentially related to pose estimation. So we want to estimate the pose of a robot, and we want to do it using velocity measurements. Then we will extend this to inertial measurements. And we want to use homographies as our visual measurement to do this. And the rest of the contributions, the perspective will change. We will not be actually doing pose estimation, but we will be estimating this homography matrix itself. So we will basically design observers to estimate this matrix, and I will show you later why it's important to also work with homographies themselves. And in the last contribution, I will also talk about something we call polar symmetry, which can be also applied to estimate the pose of a robot for specific type of problems. Okay, so now I'll start with what we call Riccati observers. So as I said, we have some moving frame here, which is CT. So this frame is attached to the camera, and we have some reference frame T0, and we have a relative position and orientation denoted by R and X as the relative pose between the two frames. And we also have a distance in a normal vector or to this plane expressed in both frames. And so if we have coordinates between the points PI0 and RPI, which are expressed either in the moving frame or in the reference frame, these coordinates can be projected from one frame to the other using the homography matrix. And this matrix is this matrix over here, so this H, which is a 3x3 matrix that encodes the relative pose between them and the structure of the planar scene, so its direction and distance. So how do we solve this problem in general? So we have our kinematics for our pose. So we assume that our velocities are measured for now. So we have an angular velocity omega and linear velocity v. And what we actually get as measurement for this type of problems is the normalized feature correspondences. So basically, instead of working with the Euclidean coordinates, we actually work with spherical coordinates, pi and pi0 expressed in 2 frames, and they are related by this constraint over here. So the problem is not really straightforward because we cannot really extract the position directly for this sort of problems. What we actually do is we estimate a scaled position. So we estimate this x over the 0 over here, and r and eta 0, and these are what we call the components of the homography. So what we're actually doing is we're extracting these components without necessarily knowing the homography itself. And in order to do that, we basically have our system, which is given over here. So this eta 0 here is a constant, the normal direction to the plane. And when we design the observer, we say we're not going to design it directly on this element on S2. Instead, we're going to over-parameterize it with some rotation matrix. So basically, I'm going to assume that my normal direction is a rotation of a fixed direction over here. Now, I will explain to you later why this actually works and what's the advantage of doing that. And so we design the observer using this rotation matrix Q hat. And once we get this Q hat, we can project back the solutions to the sphere. So what remains now is to determine these sigma innovation terms, which are in red. And in order to do that, we have to define an error for our observer. So because we're working with a Lie group, one thing we can do is we can exploit the structure of this group. So R and X bar actually belong to a group we call the special Euclidean group. And this is the group of rigid body transformations. And we can use the structure of this group to define an error, which is given over here. And we also have the rotation, which is in SO3, and we can also define an error for that one. So once we define these errors, we can simply locally parameterize these rotation matrices with some vectors, which we call lambda. And the idea is if this lambda here goes to 0, then my error rotation will converge to the identity, which means that my estimate will converge to my true rotation matrix. So then what we have to do is we sort of linearize our error equations in terms of this linearized state that we define, and we try to get a matrix that is of this form. So we have a linear system right now with a matrix with a lower triangular form. And the tricky part here is in the measurement, which is defined using the homography. So this is a nonlinear measurement. So what we do is we multiply it by this H hat matrix over here. And this H hat is, in some sense, an estimate of the homography that we reconstruct using the estimates of our state. So then we also derive a measurement equation, and we get a C matrix as well. So this A and C matrix are quite important for the observer design. So then the way we design it is we implement it as a Kalman filter. So we have our input, which is our innovations, given by this following expression. And this P matrix is solution to what we call the continuous Riccati equation, given over here. And we use a nice result from a paper on Riccati observers from 2017 by Hamill and Sampson, which says that if the matrix pair A star and C star, which are these matrices evaluated at the origin, are uniformly observable, then we can actually achieve local uniform exponential stability. So what I mean by uniform observability now is given by this definition. So we say that the matrix pair is uniformly observable if this matrix W, which is what we call the observability Gramian, is definite positive over some time interval. So if we manage to prove that, then we have the stability of our observer, and we know that the algorithm will converge. So what we need to do is we need to find conditions for this matrix pair to be uniformly observable. And in our work, what we managed to find is that we actually can find a geometric relationship. So if this condition is satisfied, then we have uniform observability. And it's actually on the number in the layout of the points on the scene. So I'll define a consistent set. So this is basically a subset of at least 4 direction vectors, such as no triplets are linearly dependent. So in this example here on the right, we can see that this is a consistent set because there is no triplet that is linearly dependent. However, in this example, we can see that this is not a consistent set. And so if we assume that we have a consistent set, then we have uniform observability, and therefore we also have the stability of the observer. So something we actually can do is since we're only estimating a scaled position, we can actually retrieve the true scale. So we can estimate this S hat over here, which is the inverse of the distance, and also a gyro bias that we can also estimate. And the idea is we cascade another observer with this Riccati observer, and we can prove the global stability of the entire state. And this, we can do it when we have velocity measurements. However, sometimes we don't have velocity measurements, so what we have to do is instead of using the velocity as an input, we're going to estimate a scaled velocity. So we can estimate this v over d0, but we can't estimate them separately. But it doesn't really matter for us. Okay, so just to show you some simulation results that we got, we simulate a camera that is moving in a circular trajectory over a horizontal target, and we run Monte Carlo simulations, and we display the estimation errors, and we see that all the estimation errors are converged. So these are the Riccati states that I've shown you earlier, and this is the bias and the scale that are also converging to 0. So then we decide to perform experiments, and in order to do that, we have a setup here in the lab. So we have a visual inertial sensor over here, which is a camera in an IMU, and it's viewing this target, and we move it, and we record the motion using a motion capture system. So now we can compare to a ground truth that we have. So we do this, and we can see here, so in blue, we have the motion capture ground truth, and in red, we have our pause estimate. So these are components for the position vector, and these are the Euler angles for the orientation. So we can see that we get some small deviations over here. And this is because the moment we start actually moving in translational motion, what happens is the assumption on the constant velocity is no longer valid. So it still converges quite consistently, but there is some, we can see that there is some deviation between them. So a solution to this is instead of using velocity measurements, we can actually use inertial measurements. So we use the accelerometer that we have in the IMU. So, but this is not very easy to do. So we have our system as previously. Now we have to include the velocity as a state. So we have our dynamics so now we go into the second order kinematics, and we have this acceleration measurement that we can inject here, but we also have the gravity component to take into consideration. And for the gravity, we model it as some constant multiplied by some direction vector. And we do the same thing for this direction vector as we did previously. So we now design another observer with another matrix we call G hat, which is like the Q hat matrix, and we're going to apply the same trick. And we can also define the error using a group. In this case, it's not the spatial Euclidean group, it's what we call the extended spatial Euclidean group. So now we can also add the velocity into the group, and we can define our errors. And in order to design the innovations, we apply exactly the same principle as before. We linearize the system, then apply the Riccati framework. So we also now have to find uniform observability conditions. So we're also going to require the consistent set condition for the states to converge. And we use uniformly consistent, which is a stronger property that will not really detail. And we also need a persistently exciting condition that needs to be satisfied on the variation of the velocity. So this sort of says that the velocity cannot be constant. So there has to be some acceleration in order for this to be satisfied. And if this is satisfied, then we can actually estimate the depth, and we can also estimate the gravity. And so we have the local stability of the filter. So we run the same experiment simulation, but this time we have like an inclined horizontal plane. So we have a gravity vector that is not necessarily known. We have a normal vector as well. And we also display the estimation errors, and we can see that everything is actually converging to 0. Okay. So now we can perform the same thing as we did before. We will do exactly the same experiment. So I will not really detail the algorithm, but in order to understand what we need is that we have the images. So we have to extract the features from these images, and then we get our PI and PI0 measurements that we need to get. And we implement the observer in a discrete format. So we have a propagation step and an update step. So in this propagation, we only use the IMU data to propagate the state. And then in the prediction or in the update, we use the visual measurements to make a correction. So just to show you, these are the results that we got for this one. So just to show you a video. So what we do in this case is we actually do what we call warping. So now I have all the states in order to reconstruct my homography estimate. And I can now evaluate my estimates using this homography. So the homography can be used to warp back all the coordinates into the reference image. So this is what we can do. So it's as if we have a constant image here, and it's the environment that is sort of moving because we're using this homography matrix. And at first we have this motion over here, so we have this motion on the U. And then we switch back to other types of motion. And as these states are actually converging to the ground truth, I can reconstruct a homography matrix and then use that matrix to do what we call warping. So the idea is simply projecting back images from one frame to the reference frame, and it feels like the reference image is not changing at all. It's just that the environment is sort of moving. So we'll not show the entire sequence, but this is sort of one of the many applications to homographies. This is what we call image stabilization, where we want to stabilize an image, and we can actually use these in like control problems and similar things. Okay. So for now, these are the contributions that I discussed for pause estimation by designing Riccati observers. I will now switch to a different perspective in this thesis, and I will not be talking about estimating the pose itself, but about estimating the homography matrix. So the first contribution in this sense is what we call a dense observer. So what I mean by an observer that estimates the homography using dense measurements is that instead of using features in the image, we can actually use the entire image as a measurement. So how do we actually design observers for the homography? So one idea is that the homography itself is defined up to a scale. So I can always inject some scale gamma over there, and this will generate always the same homography mapping. So I can choose this gamma in a way that will constrain the determinant of H to be equal to 1. And by doing so, I can ensure that this H matrix is in the special linear group, SL3. So you see we're working with a lot of Lie groups. This is one of the popular groups that we can work with. Now that we are working with a Lie group, we can do a classical observer design on a Lie group. So we can actually, so this group, element H has kinematics on the group. So it has these kinematics, H dot is equal to HU. And this U here is what we call a group velocity matrix. And it lives in the Lie algebra of the group, SL3. So this is basically a traceless matrix. So if this matrix is traceless, then this H will always remain in the group. So now for now, I'll assume that this velocity here is measured, and I can design an observer for H. And this observer is basically an internal model. So I'm going to copy the kinematics of the homography, and I'm going to add another innovation term now, which is this delta. And I want to design delta in order to ensure that this H hat converges towards my H. So to do that, we also have to define a group error again. So you see the interest of working with groups is we can define these errors on the group, and then we can use that to design our observers more accurately. And so by evaluating the dynamics of this error, we can find that it's actually autonomous, meaning that if this delta goes to 0, then the error does not evolve. And the idea is we want to design this delta such that our E goes to the identity, which means that our estimate H hat goes to the true homography H. So how can we design this delta? So the constructive approach is basically finding a suitable symmetry of this matrix on the output, so on the measurements that I have. Once I find this this action on the output, I can construct a corresponding cost function. Once I do that, I can use the gradient of this cost. So basically do a gradient descent in order to ensure that the error is converging to the identity. So a symmetry is essentially this map rho, such that if I have this relation over here, then it preserves sort of a symmetry with the homography operations itself. So just to give you an example of previous constructive designs, so this is what we call the feature-based homography observer. So you see that this, we will use exactly the same constraint as before. So we have this pi0 over here, and we can actually design our delta using a cost function that can be defined from this symmetry over here. And there's been a lot of work in this sense. Actually, there's been works on point features, lines, and also conic features. And for each, we can find a symmetry on the output space, which can then be used to construct a cost. And then we compute the gradient, and we find an appropriate correction term, delta. So what if we don't want to work with features? What if we want to work with the entire pixel information in the image? So one idea is instead of defining the action on the features themselves, you can actually define it on the intensities of the image. So the action of SL3 that I just showed you over here, this one, can actually be used to induce an action on their intensities. So instead of just mapping the feature points themselves from one image to another, I'm actually now going to map the intensity of the pixel, so the value of the pixel itself into another image. And we define this new group action here which is defined as a composition of the image function itself with the other action on the feature coordinates. Now that we have an appropriate action, we can use it to do the design that I just showed you. So the way it works is I can define an error image. So I have my image over here, which is my image I, and this image is related to my reference image using H. So I can have an H hat inverse, which will take me to an error image, which I want to convert to the reference image. So if this H hat converges to H, these images will be identical. And now what I have to do, I have to use the difference between these two images in order to design my observer. So I can define a cost function. So this cost is given by this. So it's simply the difference, the norm, the difference between the two image maps. And we have this cost. The problem is, are we sure that this cost is non-degenerate? Meaning that when this E here is equal to the identity, is this really a global minimum for this cost? So we actually derive a condition for that. So if this condition is satisfied, which means that the Hessian of this cost is non-degenerate, then we know that the identity is a global minimum. So we have a proof of this. So now we can actually use the gradient of this cost function to design our correction delta, and we find the following expression. So this R here is the intensity residual. So it's the intensity difference between the error and the reference images. And it also depends on the gradient of the error image itself. Just to show you some simulation results. So we have a reference image here at time 0, and this is sort of our moving image using a generated homography. And now what we want our error image. So we're using a warping, as I showed you before. The idea is if the estimate is converging accurately towards H, then this error image should converge towards our reference. And so this is what we see over time. So over time, what's happening is it's actually converging towards this image, and the difference between them goes to 0. The problem with this is that so far we have made the assumption that we have measurements on this U velocity that I spoke about before. The problem is that this U is not really measured. In practice, we cannot really measure it, and we actually can even find an expression for it when the scene is static, which is given by the following expression. So it depends on the rigid body velocities of the camera, but not only. It also depends on the structure of the plane. So if the configuration of the plane is different, then the group velocity will be different. And this part here, I can measure using a gyroscope, but this part here I cannot measure. So one idea is I can actually split it into a measurable and unmeasurable components and consider this gamma over here as a perturbation and try to estimate it alongside the homography. So how can we estimate this gamma? We have to make some motion assumptions to simplify its dynamics. So for example, if I assume that the derivative of x over d is constant, which means that this is a motion that is a linear motion parallel to the scene or exponentially converging towards it, then I can design another observer for h and gamma together, and it's given by the following expression. So it's actually, we have a proof that we can actually use exactly the same innovation as before, and this still holds, and this gamma will converge to 0. So we actually implemented this in a simulation, just to show you a video. So here we have our reference image, and we can see here, so initially what happens is that the red here is basically the warped image. So we have this warped image here that is supposed to converge on this reference, and this reference is basically a target that I have on my image sequence, and as I move in the video, I want this warped image here to converge towards this region of interest. And we can see here in red that as it starts evolving, the cost is actually decreasing, and we can see that the warping is actually good, which means that the estimate is converging towards the true homography. Of course, this is not perfect because the pixel coordinates are not exactly perfect. So what happens is we can see that some noise, so we can see there's some vibration in the warp image that is slightly moving, but it's still converging towards my image. Okay. So far, this was the contribution for the homography estimation problem. So before they used to use feature coordinates directly to estimate the homography, the contribution was we can actually use pixel intensities. However, another issue is we still have to make these motion assumptions to estimate the homographies. So how can we avoid doing that? So I will present to you something we call the augmented homography estimation. But before doing that, I have to go into a little bit of theory into what we call equivariant filters to explain what it is actually. So what if the state of our system is not on a Lie group, but is on what we call a homogeneous space? So a homogeneous space is basically a space on which we can find a symmetry. So a symmetry is a group in a group action such that this group action acts transitively on the group, on the space. So to give you an example, the sphere S2, which is the space of all direction vectors, is a homogeneous space on SO3, which meaning that if I have some direction vector, I can rotate it anywhere using a rotation, and I can go to any other direction vector on the sphere. And so we talk in this side about what we call equivariance. So we say that the system is equivariant if we can also find an action on the input space, not really on the state space, which is this psi action such that this condition here is satisfied. So in general, what we mean by the equivariance is that if I have some point in the manifold and I transform it into another point, the idea is that the dynamics will also be translated, but the input will change. So there's also an equivalent transformation on the input space that sort of matches the action on the state itself. And we can also do this on the output. So if we have an output y, which is h of psi, I can also find a group action on the output such that if I transform my output, it equivalently transforms the state. And so we talk about equivariant outputs as well. So why am I presenting you this? Because if the system is equivariant, we can actually do a really nice trick, which we call a lift. So what we mean by a lift is that I have my manifold over here, so my psi is evolving here, and my dynamics are sort of dictating where the state is changing. And instead of doing that on the manifold, I can actually construct a lift, which is a map that would take the dynamics into the group that I've been talking about, and then I can express the dynamics. So basically do the evolution on the group and then project down the solutions back onto the manifold. And this projection is using this phi action on the between, so it's sort of a map between the group and the manifold. And in order to do this, we sort of have to parameterize our manifold using the group. And for that, we have to fix an element here, which is this xi0. So if I fix an element, I can represent all the other elements, such as doing the dynamics on the group, then I project down the solutions. And the lift actually verifies that I can always project down the solutions correctly, so it matches exactly the same trajectory. And we can now use this to design an observer or a filter. So how does this work? Instead of doing the observer on this homogeneous space, I do it on the group. So I define my dynamics here on, so now we'll be talking on x hat and not xi hat. And so I will be defining my observer here on the group. Then I can always project back my solutions to get back my actual state estimate using so this projection here. And I can also now define what we call an equivariant error. So this error is a global parameterization now for the elements of the manifold using the group. So now that I can define this error, it's sort of equivalent to the errors I was defining on the groups, but now I have to use also the projection phi, using the phi action to define this error. So then what I have to do is I have to choose some local coordinates around this xi0 and linearize them, linearize the dynamics in order to get sort of a linearized error system. And I can do exactly the same thing for the output. So I can define an output residual, and I can use the fact that I have an output symmetry rho in order to also construct sort of an output residual expressed in terms of equivariant coordinates. And then I linearize, and I have also a sort of a linearized measurement equation. And then I simply apply a Kalman filter for this linear system. So we basically propose an innovation, and this innovation is related to the continuous Ricci equation that I showed you before. So how do we apply this to homographies? So as I showed you before, the state for now was considered as H, which was an element of SL3. What if we extend the state such that we also include these two parameters here, D and eta, which are unknown? So if we estimate everything together, we can actually reconstruct the homography in its velocity. So this is what we do. We extend our state, and we also now, what we consider as input our system is these V and omega directly. So now the rigid body velocities are direct inputs to the system, and now this state has been augmented. This is what we call the augmented homography problem. So we can actually prove that we have a symmetry group that acts on the space. This group is given by SL3, MR1. So basically, I have a homography component here. I have a rotation component and a scaling component. And I can show that these group actions actually provide me with equivariance. So I can actually do a lift for my dynamics and design the observer on this group instead of doing it on the state space. So the calculations are a bit lengthy. The expressions are very long, so I'm not going to give them to you, but they're all in the thesis. So we run some simulations for this, and we basically run a Monte Carlo simulation where we have a camera following a Lissajous trajectory, and we can see that all the estimation errors are converging to 0. So even the normal direction and the distance are all converging to 0. So we actually did another extension to this work, which was instead of actually using velocity, so linear velocity is not really measured. So we're going to do exactly what we did before. Instead of using linear velocity directly, I'm going to use acceleration. And we can actually add the velocity into the state, and we also have to add the gravity direction into the state. I decided not to put this part in the presentation, but it's all in the thesis. And we can basically do exactly the same thing and design an equivariant filter for that problem. So in order to evaluate the consistency of our filter in this case, we compute what we call the ANIS, which is the average normalized estimation error squared. And this gives us an information whether this filter is actually capturing the distribution of the estimate or not. And we can see that the ANIS of this filter actually converges slightly below the value of 1. And in general, we want this ANIS to be equal to 1. So this is sort of the ideal value that we want. Okay. So now I'm going to go to another contribution of this work. So just to summarize, the first contribution was regarding estimating the pose itself. Then we went into designing observers for estimate the homographies. And now I'm going to go back to the pose estimation problem, but from a different perspective. So I'm going to talk about what we call polar symmetry. And before talking about polar symmetry, I'll present to you epipolar geometry. So I spoke in the introduction about the different types of problems we have with monocular vision. And if the coordinates are actually in 3D space and not on a plane, we don't have a relationship between the points using a homography matrix, but it's actually given using what we call the epipolar constraint. So this constraint is always satisfied between the rotation matrix and the direction of the position vector and the bearing coordinates in the two camera frames. The problem with this constraint is that it's independent on the scale. And so because it's independent on position scale, it's not really compatible with Euclidean symmetry, where we have the rigid transformation with an orientation and complete position component. So how can we design an observer that sort of decouples the position component to have a magnitude and the direction so that the direction part would only be included in the epipolar constraint? So one idea is to use, instead of representing this vector in R3, we can actually represent it in using a Lie group called SOT3, or the scaled orthogonal transformations group, which is a group of rotations and scalings. So basically, if I have a vector and I want to go to another 3D vector, I will simply rotate that vector and scale it to go to any other point in R3 except 0. So we managed to show that we can actually have a group that acts on the pose space. This group is what we call the polar symmetry group. So it's SO3/SOT3. And what it does is basically I have my position orientation here, direction in orientation here. And I can actually transform them into a new position and orientation, a direction of position orientation into another frame. And what's happening is that I'm also transforming or re-rotating the bearings as well. And this, what it does is actually preserve sort of a structure of this epipolar constraint. And I can use that to design an observer as I did before. So how can we do that? We simply lift the pose kinematics from this space onto the Lie group SO3/SOT3, and then we fix some origin R0, X0 at a choice, and we design the corresponding equivariant filter. So for this problem, we didn't actually stop there. We were actually able to analyze its uniform observability. So meaning, when does this actually work? And we end up with two sets of assumptions. So in these assumptions, if these are satisfied, which meaning that, so I need to have at least 5 landmarks, and they need to be distributed in a certain way. So I can't have them, for example, positioned on a horopter curve, and the origin of the camera lies at the origin of this horopter. So we have different conditions on how these points have to be sort of laid out. And if these conditions are satisfied, then we can actually recover the states that are related to the epipolar geometry, which are the direction of the position and the orientation. So this is very classical to the computer vision people. Usually they have 5 points, they can extract these components. However, what about the magnitude? So for the magnitude, we actually have a uniform observability condition for that, and it's the following persistently exciting condition. So if this condition here on the velocity is satisfied, then the scale component is also uniformly observable, and so the entire state is locally exponentially stable. And what this condition says is that the only motion that is not allowed is the motion that is on the axis that is relating the two origins of the frames. So if the camera moves like this, the magnitude is not observable. But it moves into any other direction, it will be observable, and I can estimate it. So just to show you, to validate this using simulations, we do a simulation according to 3 phases. So we have a phase with no motion at all, then with non-persistently exciting motion, so the camera will move on this axis, then we do a persistently exciting motion. And we can see here that the error on the orientation in the direction actually converges directly. However, for the magnitude, so it does not converge at all in the no motion phase, and then it still not converges in the non-persistently exciting motion. But the moment we have a persistently exciting motion, we can see that it rapidly converges to 0. And the Lyapunov, the associated Lyapunov function actually also converges to 0. And so this is locally exponentially stable. Okay, so I finished with the contributions of this work. Just to summarize some of these contributions. So we basically designed Riccati observers to estimate the pose of a camera using homographies as implicit measurements. So we did not really have to estimate these homographies, but use them implicitly as measurements. We then proposed an observer solution that would estimate homographies using dense measurements. And another contribution was defining the augmented homography problem to design equivariant filters. And we do this using velocity measurements or even using inertial measurements. And the last contribution is on applying this polar symmetry group in order to estimate the pose by decoupling the position components into direction and scale. So just to talk about the perspectives of this work. So one of the perspectives is to actually use these pose estimates and integrate them into control design problems. So what is the value of having the estimates? The most important part is to use them in control applications. Another perspective is to improve the dense observer to match state-of-the-art algorithms. So for now, as it's designed, it's a bit raw for an algorithm, so it has to be improved and sort of robustified in order to match their performance. Another nice perspective is to investigate how can we actually do a visual inertial SLAM, for example, using this augmented homography EQF perspective. So the idea is that instead of estimating a pose like we do in a classical SLAM, we estimate homographies as we move, and we're also estimating sort of the structure of the planes in this environment. And then we use these homographies to sort of reconstruct the pose by extracting it from the homography matrix itself. And this will be quite interesting to explore. And one last perspective is see what are the possibilities of extending the polar symmetry parameterization. For example, in visual SLAM challenges, we're basically decoupling this position into scale and direction, sort of robustifies the algorithms in some cases. Thank you for your attention.
So thank you, Tarek. I need to. Is my mic on? Yes. I don't see. What is the Zoom? Can you hear me?
Yes, we can hear you.
My mic is not on. Can Okay, so can you hear me? Everybody can hear me? Yes, okay. So it's time for questions. So we will start with James Forbes. I leave you the stage.
Okay. Good morning. Yeah, I'm James Forbes from McGill University. Thanks very much for the really great presentation. Yeah, I just want to start off by saying, like, this is extremely comprehensive and extremely impressive, and I really think you should be really proud There's a lot of really great work here, so congratulations on that. Okay, so I want to ask some, by the way, do we have 2 rounds of questions or just 1 round of questions?
2 rounds.
Do we have 2 rounds of
No,
questions?
just 1 round. You can ask all the question you want.
Okay, okay.
Then
All
we
right.
pass to the next one and so on.
Okay, I was just clarifying. Okay, thanks. Um, okay, so could we go back to slide 8, please?
Yes.
Okay, and I just so I want to better understand the trick. I at one point you said, "Oh, I'll explain the trick in more detail," and then I feel it wasn't explained. So, we have this A to 0, and then we use this trick to essentially, rather than estimating eta
Yeah.
directly, we want to work with Q. So, can you explain this trick? Yeah, can you explain this trick a little bit for us, please?
Yes. So I explained it, but okay. Can you hear me still? Okay. So the idea is I explained it, but I did not really say that I explained it. That's the issue. So I just go back into all the theory on equivariant observers and sort of here. So what we're actually doing is a lift, but I do not say explicitly that it's a lift. So the idea is I have this eta 0 here, which lives in S2. So it's a direction vector. And I know that I have a group action of R of SO3 on this direction. So what I say is I'm going to fix one direction, which is the E3 direction, so the vertical direction pointing downward. And I'm going to represent all other directions as a rotation of this direction itself. And then instead of expressing my kinematics as eta dot is equal to minus omega cross eta, or in this case, it's a fixed direction, so it has no kinematics, I'm going to do that on the group. So I will define this Q matrix, which is sort of my group element that will represent this eta. And then I'm going to lift, so it's kinematics from this, so from the kinematics on S2 to the kinematics on SO3. And I will design the observer on SO3, and then I will project back the solutions using the expression that I gave over here. This one.
Yeah, okay. Yeah, I get it.
It's lift, but I do not explicitly say it because I hadn't really. So we do not look for equivariance here. We only look for the fact that I can actually represent this S2 element as an SO3 element, and I can always project back my solutions on S2. And this is sort of more convenient to do my observer this way.
Yeah, no, I definitely understand now. Okay, so thanks for the clarification. But I want to ask another question then. So you've done this essentially a lift. So now you have these new kinematics, which involve, Q dot, R dot, and X dot.
Yes.
But it seems like all that's driving these kinematics, well, I guess in this particular example, what's driving the kinematics is omega and V, right? Like that's
Yeah.
all. Yeah, okay. And so, okay,
Yeah.
that's fine. Yeah, okay, that's fine. And I guess so the interpretation of this sigma q is like it's some sort of angular velocity that, moves this rotation around. That's essentially.
Exactly. So I didn't really give it in detail here, but what actually happens is that I only get 2 elements of the angular velocity because all the yaw orientations around the axis eta 0 are actually not needed. So I actually need only 2 elements to sort of make sure that this direction is actually converging. So basically, I can get an infinite number of rotation matrices that will satisfy this. So all the hats that are basically rotating around E3 will.
I understand that. It's just the reason I'm pausing here for a moment is that, like, what you're calling sigma q cross is essentially some sort of angular velocity.
Yes.
But that's going to be related somehow to the true angular velocity of the vehicle. And so I feel that there's some sort of over parameterization here that's unnecessary. Could you maybe comment on this?
Yeah, so this sigma is actually not related to the angular velocity of the vehicle because this eta 0 here is fixed actually. So it's a fixed direction that I do not know. So what it actually corresponds to, it corresponds to this here. So this frame is constant and this frame is moving, and I have some normal direction that is embedded in the homography, but I do not know it. And I need to estimate it alongside the pose to get everything. The issue is, so it does not have kinematics. So you see here, if I do the lift for this one, I will get q dot equal to 0. However, the q hat itself sort of have an innovation to get autonomous aerodynamics afterwards. And if this sigma will simply ensure that q hat converges to q. That's all it will have to do. So it will not be related to the angular velocity of the vehicle.
Yeah. Okay. Now I understand. Yeah. Okay. That's okay. That clarifies that. Okay. So can we go to the slide 11, the observability analysis?
Yes.
Okay. So I wrote down on my piece of paper here how observable is observable. And what I mean by this is like usually we like to think of observability as this binary notion, like it either is or is not. But you know, like you have these two pictures here where you know you have 3 points on a line, and this is not consistent, and then you have on the right hand side like other 3 points, but you know they're quote unquote almost on a straight line. And so what I wanted to ask was is like, isn't there actually a motivation here to pick smart points, and how would you do that?
Yes. So of course, if the points are closely related, that's not really. So if in this, for example, in this example, it is observable, but it's not strongly observable in the sense that as you're talking about. It still works, but of course, the better is to have the points sort of laid out all across the image. So if the points are sort of laid out basically spaced from each other, I will have better estimates, and this will actually converge better for my observer. How do we actually ensure that? So one idea is if I do so this is done using feature extraction, right? So I have my image, I extract features. In practice, I'm not going to have 4 points. I'm actually going to, so when I talk about consistent set, I only talk about the subset with 4 directions. But of course, I can have 100 directions if I want. And in that sense, I'm always, almost always guaranteed to have observability unless I'm really end up with only 4 points and like 3 of them are really aligned or closely aligned. In that case, it would still work, but it would, in my understanding, for example, it would converge a bit slower. And I even tried this in simulations, and you can see that if the points are sort of distant from each other, this makes it converge better.
Yeah, that's what I would have expected. Okay, that's good. Okay, can we go to I want to ask a question about the Riccati observer. So I guess this is around slide 14 or yeah, whatever, right? 10, slide 10, sure.
Okay.
Unfortunately, I didn't hear, and maybe you said this, but maybe I didn't understand it. I didn't hear a justification for like, well, why are we doing a Riccati? Like, let me back up a little bit. So when it comes to estimation, you know, there's complementary filters, there's Kalman filters, there's lots of methods. So why do we want to do like if you were to sell this to a startup, like why would you want to do a Riccati observer or over like an EKF or an EQF or even just a complementary filter? Why would we do this?
Okay. So with this problem, we do it with this. So it's the type of the measurement we have. So the issue is that given our measurements, what happens is that there is no, so even if you want to do an EQF or if you want to do something else, it is quite difficult because there isn't really a symmetry to exploit using this state. So if my state is R, X bar, and this Q, so the Riccati is essentially using the group structure. So I'm actually working with SO3, I'm working with SE3, but I only want to use the structure of this constraint to sort of derive a measurement equation that works well. So I could do this using an EKF, but I don't think it would work as well. In terms of linearization, in terms of trying to derive an appropriate measurement equation for this problem, the Riccati is really suited for this type of problems. So whether it's for homographies or for similar visual problems, what happens in general is that we end up with these sort of nonlinear measurement forms. And so the way it's done here is that I have this H hat over here. This H hat is basically a reconstruction of my homography using the states. So it's R hat plus X hat. This is right. So what I do is so this is not really a group error. What I'm doing here is I compute this term, which is H tilde. And then I'm going to use some tricks in order to express it in terms of my errors. So in terms of lambda R, lambda Q, and X bar tilde. And by doing so, I'm actually end up with quite nicely represented the measurement equation. And I also end up with a minimal representation of my state. And the Riccati, for me, is a suitable choice for this type of problems.
Okay, I want to maybe try to put that in my own words then. So it sounds like the motivation here is actually like if you have the measurement in a specific form, it really leads to really nice like A and C properties that will then have some really nice convergence results. Is that a
Yes.
good summary?
And even if you do this using another design, the C matrix will come up with for the recurring, or for like for an EKF will not be. So in all the time, you'll always end up with a C matrix. So you're actually making the trade-off. So in our case, the A matrix is actually quite nice because our state is just opposed in a direction. However, my measurement is quite complex because I have nonlinear sort of constraints between set of points related by homography. So I will end up with a C matrix that is quite complex. However, it is well suited for the analysis of the observer. And in this case, I actually want to have a C matrix that is complex because even the observability analysis is only done using the C matrix. This is actually sort of a geometric condition. It does not require motion at all. So I only use the C matrix for the observability analysis.
Right. Okay. Can we maybe jump forward to slide 20?
Yes.
And I'll try to only answer maybe one or two more questions because we don't want to be here for too long. Okay, so so what I wrote down how did you actually discretize this like in practice? Like you actually have to discretize the Riccati observer as well.
Yep.
And like we all kind of know that like there's continuous time Riccati equations and there's discrete time Riccati equations, right? And so I'm just wondering, did you have some clever tricks there as well, or did you kind of like the classic, just Euler discretization basically?
So there were some tricks that needed to be done. So just to tell you about some of the tricks that we actually did. So actually the propagation step is just sort of a numerical integration of the dynamics, or at least the pre-observer dynamics, and then we get our propagation. For the update, we actually implemented it as a discrete Kalman filter. So we have our K matrix and we simply implement it. However, we actually ended up with doing a trick which happens to be similar to the iterated EKF, where we actually run the update multiple times for it to work. So this actually had to be done in order for sort of the observer to converge because all the information we get is actually in the measurement. So it's in the image. And when we actually do only one step, the image does not really converge properly. So if you do it in multiple steps, so like on 100 step or something, it will progressively converge. And this was one of the tricks that we actually did for this implementation.
Okay, great. Yeah, actually, I'm not surprised to hear that. Because in everything I've done with this, yeah, if you don't iterate, it never works. Okay, that's fine. Okay, one other thing is that I didn't really see in the videos. Can you go to the video, just the next slide, slide 21? Um, yeah, so actually, I want to ask about that. So why did you do that? What's with the piece of paper in the front?
Yeah, that's basically. Let's say that I want to abstract the vision, see if I still get features. And so one of the ideas was, okay, if you have an image here, then you will have less features, and will this work with less features? This is sort of the idea. You will still get features, but not as many as if you have the full image. And then the rest is just doing motion and trying to record this motion. So here you have the CO, then you have the pitch, roll angle, and pitch and roll angle.
Okay, but here's what I want to ask though is like what about occlusions during motion? Like and also like I didn't see the camera actually like at no point did I see the target have less than like 80% of what you originally saw. Like where I'm going at with this is like how robust is this really? Like if you move the camera aggressively such that you only have 20% of the original image there, or if you are moving around and you now take that piece of paper over it during moving around, like is it really that robust? Because like in my experience, the the robustness is a problem sometimes.
So So robustness in this case is actually related again. So if you talk about the occlusion in this case, do I have enough features for it to work? It will not work as good as it does like if I have the full scene that is being observed, but it will still converge. And one advantage, in my opinion, for this type of observers is that even if at some point you actually lose, let's say that I lose the entire object, so I see nothing, it will still sort of not diverge because I'm doing a propagation step using my IMU. So I'm using some angular velocity information, I'm using some velocity, so in this case, even acceleration information, and this sort of keeps the image sort of close, or at least the camera estimates sort of close to the true ground truth. So then when I have vision again, or when I have my scene again, I can actually converge back. And even in the sequences, maybe here I just showed these parts, actually you can end up with quite severe motion, and even with some occlusion, it will not always work, but it will not just abruptly diverge, it will actually still converge in some, will be closely converging, and then it will converge again to my image once I have. So there is some sort of temporal correlation between the previous information and the information I get now.
Yeah, it would have been nice to see though, right? Like that sort of robustness is, I feel, practically important. So it would have been nice to see videos on that. But
Yeah.
that's okay. Okay, so maybe let's move on to the last thing I want to ask and then give everyone else a chance. So I want to ask a question about the whole direct measurement errors, actually using the pixel errors. And so yeah, yes. So I want to ask about this slide. So in my group, we actually tried this and it didn't work and we basically gave up. But now I'm realizing that we weren't doing exactly what you were doing. We were essentially using what you called R on the slide as essentially an innovation. But you're not using R, you're using delta. And so I want to better understand like where is this cost function involving like the integral, blah blah blah. Like where does this come from? What's the motivation? Why do we need it? Like why can't you just take the error to be what you're calling Rx here? And then also practically, how do you actually compute this thing, right? Like pixels are like discrete, like this integral can't be evaluated exactly. Like I want to better understand how, like why do you need this?
Okay, so this cost itself. Yeah. So this cost matrix itself. Yeah. So the thing with this cost function is it's not uncommon. It's actually what the people who do dense observers and the computer vision literature do. So it's basically, I'm just here defining it in continuous time, but it's sort of a sum of squared errors between the pixels and the error image. They also call it the warped image and the reference image. And we simply define it as a cost function. For them, it's more of an optimization problem where they have this cost. They try to find some iterative algorithm that would converge, that will make the homography estimates converge towards the true homography. So you spoke about this Rx, right? Maybe I didn't hear you right. Okay, so for this Rx here, this actually came out naturally from the computing or doing the derivation as a constructive design. So you actually have this cost, you compute the derivative to get a gradient, and actually when computing this, you end up with this term over here that reappears. This is, it just appears as sort of the difference between the intensities. And if this is actually 0, it means that my error image actually converts to my reference image, if it is valid for all the pixels. Yeah, so this is actually we just took the gradient of this cost, and I forgot you had the question, sorry.
No, you basically answered it. That's fine. Okay. Yeah, I'll just say finally, like, yeah, this was really great work. Thanks for the great talk and thanks for answering my questions. And I'll pass it off to the next examiner. Thank you.
Thank you. Thank you.
Okay, thank you. So I give the stage to Sylvain for the next question.
Thank you. So first, would like to congratulate you on the work. I really enjoyed the manuscript.
Thank you.
It was well written, it was comprehensive, and there were interesting ideas such as overparameterization, decoupling, position, the virtual velocity tree, and the electricity work.
Yeah, I actually have it in the slides in the appendix, but if you want, I can have it.
And so yeah, there was a lot of nice ideas, and also there were experiments, which
Yeah.
is great. So it's a great work. It's deep, it's thorough, it's rigorous. So good. Now I'd like to ask you a few questions. So I have one main critique that I put in my report, and that also appears here in the talk, which is the absence of comparison with other methods. So maybe maybe general BIO methods. Why not?
Yes.
But even if you stick to those equations and setting, you could divide many other observers. There are many techniques that exist, and all you do is just show curves, and you see the error goes to zero, and you're happy to maybe go to zero twice faster. So
Yeah, I totally, and I think this is also a motivation to sort of sell these observers compared to classical EKFs or compared to other types of. So we can actually design. So I should have done this for the Riccati observer, for example, but what I did for the Riccati, and I didn't really put in the thesis, is I compared it mostly to previous work. So in the previous work, which was done by our group, it was mostly of a homography estimation problem, then decomposition. So there were two observers, one estimates homography, the other one decomposes it. And I had these compared with the Riccati observers. We can actually see that they perform as well. So this was for me. So one of the motivations was because when I got here and I started doing the work on, at least for the Riccati part, everyone was doing this. So everyone was estimating homography, then decomposing it. So one of the contributions was to actually do this without knowing the homography. And we sort of did that part of the work. I compared it to some of these algorithms that existed, but I actually didn't derive my own, like other types as an EKF and compare it to it. But that would have been quite interesting to see, especially to see in the transient if there is better performance or there is anything that the Riccati is better at compared to these observers. For the homography, so for the EQF, we can go back here. Yeah, for this one. So for this one, we actually did an EKF, but that EKF did not work well. And because it did not work well, it did not work well at all. So even in the paper, we didn't want to put that comparison with that EKF because we thought maybe there is a better implementation for a proper EKF that would be implemented. So the way we did it is that the H was parameterized as 9 elements. And then in the eta was as a vector, so you have also 3 elements. The problem is you linearize and you end up with not very nice equations, and it was not even as an EKF, it was not very stable, so it would easily diverge in the process. And that was one of the reasons why we wanted to compare to something that is comparable. So there is actually a work from Forbes's group. There is a student of his who did a work on homographies, but it was not like this. It was more on using the assumption so it was similar to this one. Yeah, this, but with features. So it's like what I showed earlier. And I was interested in comparing to it, at least some of our work, but I haven't really gotten the chance yet. And they actually do it using something like an IEKF, where they parameterize the homography as an element in the group, and then they use the exponentials, and they only do the observer by linearizing, while the previous work was this. So you do it constructively instead of doing the linearization. But yeah, I think one of the things that I really want to focus on is one part is to also see the sort of what are the worst points of these algorithms in order to how to improve them practically. Because even though the theory is good, I've realized, especially working with the DEMS and these sort of observers, that you cannot really compare to state-of-the-art algorithms unless you have a lot of robustification. You have to add, I didn't talk about this, but you have to do smoothing techniques and other tricks in order to make it converge better. And that part for me was more of now in a perspective. By working on different things, I didn't really get much time to compare each algorithm properly, but this, for me, this is still a continuous work that I wish to pursue in this direction.
But even if you don't consider that H is a matrix with elements and you just do an EKF like this,
Yeah.
you could use your structure and do an EKF on groups.
Yes.
You don't try that, like
So-
sort of multiplicative EKF,
So for this one or for the Ricari?
whatever.
So for this one, I didn't what I wanted to do was to do something like this. So instead of representing H as people do, I actually use a Lie group structure for H and sort of implement it as an MEKF, but I haven't done that yet. So this is not really published yet, but the plan for this one is to actually implement it with comparisons with similar algorithms.
Because I assume that even if you do an EKF on Lie groups, it will be a contribution.
Yes.
So you can sell two observers,
Yeah.
maybe.
Yeah, I mean, and also it shows why even by doing EKF on Lie groups, whether it's better to do this using the equivariance or not, if it actually brings value to this sort of problems.
We will come back to that, but just before, what is the difference between a Riccati observer and an EKF?
For an EKF, basically.
Yes.
So in the classical Riccati observer, or like for the theorem, or
Like the one you did at the beginning.
so it is an EKF, but for a specific class of systems in a sense. So the Riccati has a proof of convergence when the system, when it's linearized, has this sort of form. And when the A matrix still depends on the state, but part of the state is actually bounded. So it was done as a proof for a class of systems in which you have this part of the state that is bounded and part of the state that is not bounded. And you end up with this form of matrices for A and C. And the main really advantage of the Riccati is the theorem that I give here. So it does have a proof of convergence of stability, which is simply related to evaluating the observability. So if I have the uniform observability not at the state but at the origin, then I have.
But you have the observability
In this one, yes,
Yes.
because so for
The
this,
C is invertible.
yes. And it's because what we're actually doing, so homography is actually 8 parameters, and my state is 8 parameters, and it is nonlinear, but we'll end up with something that is static. So even without motion, it works, and it works really well.
Yes, I have a question. It's going to surprise you. You said on slide 4 that using those geometric observers allow you to handle nonlinearities more naturally. What do
Yes.
you mean?
So what I mean here is simply expressing because I express the dynamics on the Lie groups.
Why is it more natural?
For me, because I'm actually working on the manifold of the state rather than just if I represent it as something embedded in Rn, or if I actually express it as something, it's sort of implicitly adding the constraints on for the state. So for example,
It's a representation issue.
yes, for me, the nonlinearity comes precisely from that, because the equations are not highly nonlinear like other problems, but it's more of a how do I represent my state more naturally. This is sort of what I meant.
And I have one last question about equivalent observers. So if you move to the equivalent observer, so you have this whole methodology. What are the theoretical properties? What are the
Here?
Yes. What I mean, all right. You have this lift and so on, and then you end up with how to compute an observer, right?
Yes.
But does this observer have properties?
Yes. So the error dynamics, for example, are not really autonomous, but they are, for example, in general, they would be independent on, like, for example, so everything is represented with respect to this state over here. Or at least the xi0 that I didn't write. Yeah, this. So actually, when you compute the error dynamics, you end up with something that is not autonomous, but it's quite nice. So when I linearize it, it's not really exact linearization like we have with the IEKF, but I get something that is quite nice. So the linearization is better than if I do something else, because I'm not really linearizing around the state estimate, but I'm actually doing it around some fixed origin that I choose myself. So for me, this is a huge advantage for the EQF in this sense. It's like I'm doing it when I do on the group and I linearize around the identity. It's sort of an extension of that property to these type of spaces.
And other properties like
I mean, it does have like stability and it converges faster than. I mean, if I would design an EKF and EQF, I would expect an EQF to converge faster because the linearization for me should be better. This is where I spoke about more naturally representing the state, in the sense that if I represent it using the group and I actually do linearization around the group, this should be better than if I did the observer directly on the manifold.
Should be.
Well, it has to be. It is. I mean, theoretically, it is better. Practically, yeah, I didn't show it by comparisons, but
Okay, thank you very much.
thank you.
Thank you.
So
So
the next question would be Pascal.
Pascal.
Okay,
You
thank you. Yes, thank you, Mr. President. So first of all, I would like to congratulate also Tarek for the work. That's very nice work. I really enjoyed reading the manuscript. Also, there's a very nice chapter at the beginning and very complete chapter on observability estimation. So that's also a nice part before all the contribution, the personal contribution of Tarek. I won't have many questions, but a few. My first question is kind of general question about the first part of the thesis. In fact, it's not only related to your work, Tarek, but it's a little bit more general. So essentially, the Riccati observers are basically linear observers, or those based on linear time varying systems. And each time you design an observer, basically you have to do an observability analysis. And when we see the observability conditions, basically we find the conditions, the classical conditions that you also get when you design a nonlinear observer. For example, the set of points, the 4 points which have a specific characteristics, you see. That's also the conditions that appear in previous papers, for example, Mindyk and co-authors. And so my question is basically, is there a way to avoid doing each time these observability analysis? Is there a way to basically say, okay, we have an intrinsic observability property when we have this kind of problems with the specific state that we want to estimate, a specific measurement? Is there a way to appeal basically to a general observability property that will not depend on the specific observer that you are building at that moment? I don't know if you understand my questions.
Yeah, I sort of understand the question. I mean, for at least for this problem of homographies, for me, exactly. So the first thing I realized when we had this condition was that it's exactly similar to the ones that do homography observers. And even the people in computer vision, they say that if you need a minimum of 4 points to estimate the homography. So it's always repeated that if I have a minimum of 4 points, I can always get a homography. For me, for this observer in particular, it's the state itself is not the homography, but it's its components. And it's sort of natural if I can recover the homography and it's not singular, then indirectly it means that I can get my full state. And the proof is sort of, it uses this in some sense. About your question about whether we can find some, are we talking about like observability criterias or sort of something that avoids doing this analysis?
Yes, basically something that avoids doing each time the observability analysis on the matrices A and C, you see. Because basically we end up each time with the same conditions. That's also the same essentially when you add the velocity estimation, when you have a persistency of excitation condition, and that's also the same kind of conditions that we get in other works on homography, on this problem of basically estimating homography or opposed based on measurement relative to a planar target. See.
Yes.
So essentially, I think we waste a lot of time doing all this analysis, which is basically very technically, and every time ends up on the same conditions. So there's something intrinsic in this problem, and I think we waste a lot of time doing all that work.
I agree. I did this myself. Just to answer your question, I do believe that because the condition for the homography itself, for example, is sort of algebraic, there should be a way sort of to say, okay, I have a problem that does not necessarily estimate homography, but it requires it to be observable. Then the criteria should directly correspond to the 4 points criteria, at least but for the uniform consistent set and everything. Also, for the persistence of excitation, I'm not sure if we always end up with the same thing, but I think when working with accelerometers, as well, at least we have this gravity component that appears. We have generally these conditions on the acceleration, and I wouldn't be able to say whether we can find something that's generalizable, but maybe there is something that would simplify the observability analysis in the sense that instead of like dealing with my A and C matrices, I only consider the C matrix because I know that like only that part really matters for me. Or in some cases, I work like with the homography EQF, where we can actually see directly that if I have no velocity, it will diverge. I'm not sure. Maybe there is something there. For me, the problem is that the designs are not always identical. So some properties are particular to some problems, but maybe there is something that can be generalizable in that sense.
Okay. I had a small, just technical questions, just something that I didn't grasp when I read it. So you can go to the slide 26. So that was relative to the stability analysis with this innovation, because basically in the thesis, I mean, you go very fast. You say, okay, the derivative of basically it's on page 118 and 119. You say, okay, the derivative of my basically Lyapunov function is a semi-definite negative, and I conclude with LaSalle.
I didn't.
And you say basically I conclude with LaSalle, but you don't provide any detail. So it was not completely obvious to me that it was so straightforward. So I don't know if you can. Basically, it's at the top of page 119. Say the time derivative c dot. It's relative to this innovation. You see, it's really on this part.
Yeah. This expression.
Yeah. It's with this expression. You say the time derivative is negative semi-definite and equal to 0 when delta is equal to 0. This implies by application of LaSalle that delta converges asymptotically to 0, and so you conclude that the equilibrium is locally asymptotically stable. So basically, you mean that delta is equal to 0 only if E3 is equal to the identity?
So because the Lyapunov function, so yes, the Lyapunov function, when I compute the derivative, I can actually see that it converges. So I think it gives minus the norm of delta squared. And we can actually see that if delta is equal to 0, then this derivative is actually 0. And what happens is that it converges directly. So I know that the only, basically this cost here, I know that it can only converge to the identity. And so if it converges to the identity, then I conclude for the identity to be locally asymptotically stable, I think.
Okay, so basically delta is equal to 0 only if I is equal to I0.
I think I didn't here, but yeah. So these are the aerodynamics actually.
Okay.
But are we talking about the condition? It's only about
yes, that's relative to this condition, but you know that's not exactly the same term because you have the R of X before the gradient.
Yeah. There is but yeah, so if this condition actually is satisfied. So what we say actually is we say that this has to be satisfied for all the pixels. And in some sense, if this R is here is equal to 0, it means that I'm actually converging to my image because my error is actually equal to the reference.
Yeah, sure.
And this condition sort of ensures that this here is a global minimum. And then when we do the derivation for the Lyapunov function, we simply try to analyze its behavior. And we see that it only depends on delta, and this delta is sort of pushing this E to equal to the identity. And then if delta is equal to 0, then I conclude the stability, basically. But I think maybe I didn't write it properly, so I will recheck it.
Yeah. Maybe a few details there would be useful. Okay. Yes. So there was already that was the main remark of Silver about the comparisons. I also feel that's a little bit missing because I mean there are a lot of contributions and that very nice work, but of course since there's already been many things on the homography estimation problems and related problems, it would be good, I mean, to add some to compare a little bit with previous work to understand if it gives significantly different results. Maybe yes, to discuss more on possible advantages of the new design. You see, that I think that's important also.
Yeah. If for me, this here I didn't talk about this, but and this here we actually compare to the ESM algorithm of Malis, and so we consider the ESM to be a ground truth in some sense. So this green actually here means that it's actually converging as sort of a ground truth because it's a really good algorithm, and we sort of compare and we evaluate whether the dense is actually matching sort of this performance. It still lacks because we have some noise, for example, but I have other works where we actually try to improve it and smooth it in order to work better. But yeah, so I think comparisons for me is at least for this dense algorithm, because the only way to actually validate it is to compare it with a lot of the algorithms that exist in the literature. So for the homography, as I said, one of the issues we had is that I compared it to the homography estimation problems. However, what we're not doing is for the Riccati, we were not doing homography estimation. We were doing pause estimation. So I looked for work that does similar things, but there weren't really much work going on. So one thing that I considered doing, but I did not really take much time on, is what Silver suggested, which was to sort of, instead of doing a Riccati, you do it as an EKF and you apply that and you see if the Riccati is actually better. So this is actually something that is on my mind and I want to implement it as well. And finally, for this one, I also tried to implement this compared to other algorithms, but the issue is that all the other algorithms do not do this. So they do not have velocity measurements. So one possibility is to actually implement the other one, which is this. So this is the extension using actually acceleration, and compare this with the algorithms that make the assumptions on the velocity and see if using the physical measurements is actually better than not using it.
But basically, on the first contribution, yes, a simple comparison is just to take homography estimates from previous methods to do extractions and to compare the extractions, so that you can have some. I mean, so you have an easy way. I mean, to at least to compare what you obtain from what could be obtained from homography estimates.
Yes, I actually did that. I didn't include it, but I did. The first thing I did when I started working on this was to compare to the previous work on homography estimation and decomposition. I will consider at least putting some comparisons on that sense with the results that I have.
Okay. Okay, so I think that's all for me. And again, congratulations for this very nice work.
Thank you, Pascal. So I leave the stage to Robert Mahoney. Robert, can you ask your question?
Hello, can you hear me?
Yes.
Fantastic. So again, I'd just like to start by congratulating you on the body of work. I think it's an excellent PhD thesis. I'd also like to say what a pleasure it's been to work with you on some of this work, and the enjoyment I've seen from seeing you mature from a student to I would say a professional researcher, and you've given a very good presentation. So congratulations.
Thank you so much.
So there's a couple of questions I've got in there. So if you just want to jump through to slide 39. There's a statement here that surprised me here. You say the Lyapunov function epsilon sigma minus 1 epsilon converges exponentially when the full state is uniformly observable. So this sigma here is coming out of a Riccardi equation, isn't it?
Yes.
So, I mean, I admittedly it is like nearly 1 o'clock in the morning, so I might not be thinking quite straight, but normally you don't get convergence of such an object, right? So what's actually going on here is it really converging to zero, or should it be balancing the noise? This is
noise free. I did it as a deterministic observer.
Okay, so that means that the so what's actually going on with sigma then, right? So you there's no system noise, is that correct?
Yes, exactly.
Right, so the sigma should be converging to zero, shouldn't it? Right, because I mean, you keep getting information, so your B matrix goes to zero, so shouldn't it go to zero? So sigma minus 1 should go to infinity.
No, so you mean when it's not observable?
So there's no noise in this situation, right?
Yes.
So your Riccardi equation just looks like sigma dot equals, you know, the A sigma plus sigma A transpose. And then you get a minus sigma, a quadratic sigma term. So that's making sigma go to zero.
Yes.
And there's nothing that's making sigma stay positive, right?
So there is a term. So what I actually did is you have, so the problem is actually the opposite. So what happens if I have the M matrix basically, which is what's keeping sigma sort of positive. So the matrix M and N are not really covariances, but they're still positive definite, both of them.
Okay, so there's just a driving term in the sigma that you add arbitrarily to keep it positive definite, right? And then that comes out of the basically the Riccardi. So it's sort of like stochastically as though you're modeling noise, but you're saying that there's no noise, and so consequently you get the epsilon going to zero. So you have no noise in the system, but you model noise in the model, and so effectively you get this zero convergence. Yeah.
Yes, exactly.
Yeah, that sort of makes sense. So a couple of places in the report and also in your talk, you talked about gradient descent. In particular of the image, you're taking a gradient. So gradients are funny things, right? So they need a metric, and there's no inherent metric in most of this symmetry. So exactly what do you mean by a gradient in this situation? What's the underlying metric, I guess it would be my question.
You mean for the gradient of the cost?
Yeah. So, I mean, a gradient of a cost it depends on a Riemannian metric, right?
Well,
so,
the idea here is actually to define image functions as L2 functions. So the gradient is sort of related to the inner product of that sort of definition.
So, all right, and geometrically, is that metric? Does that metric have any symmetry properties with respect to the symmetry that you're applying?
It does, because they have this symmetry over here. So this symmetry is actually on the image functions, and the image function is sort of defined. So the metric is defined on the image function itself, at least theoretically. And so the metric is sort of it's sort of injected here. So this is defined as a using this. I don't know.
Yeah, I mean, it's sort of like because the image is sitting in some sort of Euclidean space, a Hilbert space, right? And you just have a basis for it. So you're taking a differential in that basis and you're calling it a gradient.
Yes.
And I guess my underlying question would be whether or not that actually has anything to do with the underlying symmetry of the problem, because symmetries often don't play nicely with metrics, right?
Yes.
Yeah. I can't think that through at the moment, but yeah, it's an interesting question. But well, let's leave that one. Let me ask you, I won't ask many questions because I don't have it in me tonight, but one last question. So in the epipolar work, right?
Yeah.
So you go to this polar symmetry, right? And you have a lift function.
Yes. Yeah.
And so the lift function is quite nonlinear, right? So I guess the question I'm asking, and it comes back a little bit to Sylvain's question about comparisons as well. What's your sort of perspective on the trade-off between making the kinematics of the system more nonlinear in order to get something nice in terms of your epipolar symmetry compared to keeping what are quite nice kinematics on SE3 or SE23 and not having a nonlinear measurement function in the epipolar problem?
Yeah, that's the question to answer. For me, it's not like the drawback of the polar symmetry, but it's because we're forcing this symmetry and we're constructing a virtual lift and we're adding a lot of nonlinearity on the dynamics. And even when we linearize, we actually end up with something that's not necessarily very nice. But as you said, the trade-off is that the measurement has this nice symmetry property, which then we can use. I think one thing would be related to what motion I'll be expecting from the camera, because the way I see it is, at least with this symmetry, we're sort of doing something similar to what the vision people do, where they have this sort of like the parametrization of the direction of the position vector, and they actually have these algorithms that they built to estimate at least R and the direction algebraically, and then the scale they try to recover that using some other information. So I don't know if this symmetry is necessarily better than the Euclidean symmetry for all problems, but I think that even though I have some nonlinearity on the dynamics, it should not be a drawback compared to what I gain in terms of symmetry on the outputs. At least if the only measurement I have is epipolar.
And I mean, I guess given that I'm a co-author on the paper, I'm equally susceptible to this critique, but we have no simulation or any sort of comparative study to prove that what we're doing makes any sense, right?
Yes. The one thing which I actually didn't finish, which I should have done, is to compare to the other observer that is done on the Euclidean symmetry, which was the one that Mihduk did with Tarek a few years ago. And that one is, for me, is the best something we can actually compare to, because we estimate the entire pose. We don't decouple the position. They actually gain in terms of observability because they only require 3 points, but the measurement equation is not very nice. So I think for me, the logical step is to actually compare both algorithms and see if the polar symmetry actually brings something to the table in different scenarios.
Okay, so thank you very much. I might leave it there. Thank you.
Thank you.
Thank you, Rob. So now I leave the stage to Peter.
Thanks a lot. Tarek, firstly, great presentation. Really enjoyed your thesis.
Thank you.
I lots of questions, but they're mostly out of interest than criticisms. One question that sticks out to me, and is one that's also been on my mind in a lot of, so of course we've had related work, is you mention in the Riccati observables, you make a big deal out of uniform observability. But it's uniformly observable. So what exactly is uniformly observable? What system is uniformly observable?
So the system that is uniformly observable is the linearized error system.
Right. And then does that actually relate to the observability or uniform observability of the original system?
Yes.
How?
So it's not really uniform observability of the actual system, but more of a stability of the observer itself. And the thing is, at least in the way I see it in terms of the Riccati, is we say that it's the uniform observability of the error system, but we're actually evaluating the system at the origin. So it's actually, in some way, we're analyzing the uniform observability of the true system, because we actually evaluated when this error here is 0. So this matrix sort of independent on the estimate, but it's actually the true. That's why in the conditions I end up with I'll show you here. So the condition here is not on the estimate, but on the true velocity term. So if this acceleration here, the physical acceleration, is different than 0, then I would have this uniform observability. And sort of the idea is you analyze it there, and then if it works, then you have some small neighborhood in which if the error is small enough, that this will sort of generalize.
But then are the A and the C here independent of your X hat?
Yes.
Okay.
I evaluate them when X hat is equal to X.
Okay, but they depend on X.
Exactly. So the condition
Or
will be on X.
equivalently depend on X hat.
Exactly. Yes. Yes.
Okay. Maybe just one other thing that stuck out to me is you mentioned the average niece on one of your slides.
Yes.
And you said it should be 1.
Yes.
But it isn't.
Yeah. It's
why?
Well, I mean, there also needs to be some tuning for this. So I implemented it the way I did, but I did not necessarily tune it appropriately. But yeah, so one thing I was looking for metrics too, because I did not do any observability analysis or anything to assess its stability, and I did it purely as a stochastic filter. So I was injecting noise and see how it behaves. And Rob was actually the one that told me about the niece, and I sort of wanted to see if it actually converges to something close to 1, and it did, but I didn't really. How do I say? Yeah, the idea was to actually compare the niece with the niece of an EKF or with something else, and see if there is better behavior in that direction.
Right.
Thank you.
Leave it there.
Thanks
a lot.
Thank you so much.
Thank you, Peter. So
Now, before leaving the word to Tarek for the final.
I have a question.
Okay. No, before
I have a question as well.
I have 2 questions mainly. So the first one is related to your similarity or comparison with the gradient descent. So at the end, what you prove is that the gradient will be 0. But this doesn't mean that you have actually true homology, because the gradient 0 can be also a local minima.
Yes.
Your cost function. So do you have any hints or any idea that your parameterization, your parameterization will avoid more local minima? So something like for this, the comparison with other methods would be
Yeah. The only way to tell is if you compare it, but it's very susceptible to, at least the way it is, it can easily fall in local minimas for sure.
Yes, so your observability is more related on the minimum number of information that you need to converge.
Yes.
Doesn't give you any hints, for example, how much must be superposed the current and the reference image to guarantee convergence.
Yeah, I
Can
think
you get it from the observability study or?
no. So what we actually get is this condition here, which only says that I need to get enough gradient information in the image for this cost to be non-degenerate. So at least for the identity,
the gradient converge to 0.
Yes, exactly. But there isn't really like a convergence proof that says that, okay, if like this is not guaranteed to always converge from any initial condition, because I don't really have a metric sort of to I mean, one thing I explored was purely experimental, was not theoretical, but was to do smoothing techniques and to sort of blur the image and try to play at least to make the gradient smoother, to make the convergence better. But yeah, I actually did some work which I did not really talk about, which was like the orthogonal decomposition. So basically this gradient, we also played with it a bit to see if we can end up with better gradient terms that will converge better if I tune them better. Because here this is just sort of a constant gain multiplied by this 3x3 matrix. And we also try to use the Hessian, the inverse of the Hessian matrix. It works better, but I cannot really characterize how well it does because I haven't compared it much to other algorithms.
And the other question I had is related to this, but concerning the perspective about Islam.
Yes.
Because so if you transpose your idea of overparameterization, for example, if you consider the world is piecewise planar and you get n normal to the plane.
Exactly.
So you mean you doing your overparameterization for one plane, okay, just one parameter more because you instead of a normal vector, unit vector, you have 2 degrees of freedom. You go for a rotation, so it's free, so you have just one. But when you have 1,000 of points because you're doing SLAM reconstructing your environment, you get thousands of variables more. And again, the case of the local minima is true, is known that the more unknown you have, the high dimensional is the space, the more likely is that you get stuck in the local minima. So do you think that this overparameterization would be also suitable for this kind of problem? Or?
So it's for this EQF, right? So basically try.
In general,
So for me,
whatever you use after, just add a parameter more, which looks like nice from one side, but on the other side.
Well, for me, this is interesting because instead of getting some, at least if we assume that we have a piecewise planar environment, then we can actually, these two parameters are the only thing we need to parameterize that plane. So I can get n parameters of these, and I will parameterize different planes, and I will also get different homographies as I move. And for me, then the rest, if I want to get the pose, it's more of an averaging thing where I extract the pose from different homographies, and I sort of refine it to get better estimates over time.
But do you agree that you get a rotation matrix for each plane?
Yes.
Which is different. So you have more known that if you just consider the normal to the planes.
Yes. But for me, the fact that for each homography, I actually get a rotation matrix, this could improve the rotation estimate itself by using the information from each plane. And once I get different orientations, I can maybe refine or average them out to get a better estimate of my rotation. So it will not be very optimized in terms of computing, but it will be at least I could get better. For me, from my understanding, it would be more robust to, if I lost the orientation estimate at a point, I can actually recover it because I have it's eventually encoded in every homography matrix that I use.
Unless you get stuck in a local minima, in this case,
yeah.
This is a question about is it better to have less parameters and maybe a worse estimation, but you don't get stuck to a local minima. This is compromise with. Okay, so no more questions. I forgot to tell you, but
thank you.
It was very nice. The last word.
Yeah, I would like to thank Bouazza. I can't say his introduction. Sorry for that. Yeah, when he left the lab, after 1 year he was good. After the second year he became very good. And the last year I guess is excellent. And he has to maintain now this level. But yeah. I will not say more than that, but I will ask him a question. Really, maybe it help everyone maybe to understand what's the difference between the CAT-V and the EQF at the same time, and answer all the equations. Because when he talked about take two direction as to how to do the minimum representation
between the two. Yeah,
this is one answer that you have to deal with. And the other one, I go back to this case, exactly this case. You have H as a state. right? I have eta is a local state, and D is an additional state. So I can define the group in SL3, and I define the other SL3. I can define also I do the lift for eta and work on SE3. And then for the D is the scalar, just do the difference. Okay. And then we can go back to the recursive. Why not? Because we didn't do the recursive for this. Yes. Okay, we did the EQF and makes things a bit more complicated. Yeah. But you can see it when you work with SL3 and SO3 and the difference. You can get also a nice linearization and so on. Now, what's the real difference between them?
So for me, it's mostly in terms of decoupling the information. So with the EQF, we're actually working with the symmetry group. So we're sort of trying to couple everything together. But at least for me, for example, I tried to, in simulation, to see, for example, what happened if the velocity is 0. Will this actually diverge? And you can actually see that, for example, homography converges and the eta also converges. But the distance will not sort of not be observable. But for me, if you do a Riccati that way, it would simplify the equations, but not necessarily the robustness, at least in some cases where I can't really recover the eta and the D in cases where I have no velocity or things like that. I think, yeah. Yeah, in this case, if I have omega equal to 0, I will get anything. Only the H, but this will be purely algebraic. It will not be dynamic. Yeah, it adds coupling, but that coupling has value. So this for me is, yeah. And for the question about the EQF and the Riccati, for me, it's different ways of viewing the problem in which either I look more into the symmetry and I want to design something using this equivariance property. And in this case, for example, it couples the entire problem, but I end up with matrices in this problem, at least the A matrix is quite complex, but I don't mind that because this allows me to use the velocity measurements. For the Riccati, for me, the main motivation was the measurement itself. So the pose state is very easy to deal with. Everyone can do that. But to design an EKF or an IEKF or something similar when working with the homography errors or the epipolar constraint, it's not very easy to do that. And for me, the Riccati is a suitable choice. It doesn't really, it's not probably, I don't know if it's the ideal solution, but for me, it's the most suited solution for this type of problems. This is sort of what I believe.
Okay, so we can stop here. Thank you again.
Thank you.
We have to know to deliberate. Thank you. On reste ici, on reste ici sur la connexion peut-être.
Est-ce que vous... Can you hear me now?
Okay. So stay here to...
Can you hear me? Rob, Pascal? I don't know. Yeah.
Yes, we can hear you, Tarek. The rest of the room's pretty hard.
Yeah, I just need